Okay, our first speaker is Julia Lockwood from UK Met Office, who will be speaking on multi-year forecasting at the Met Office Hadley Center.
Okay, yeah. So thank you very much for inviting me to speak here today. I'm going to attempt to give an overview of multi-year forecasting at the Met Office. So this is work carried out by a large number of people, in particular Doug Smith and other members of the decadal prediction team, but there were many others involved as well. And I'll start by introducing the Met Office's decadal prediction system, DEPRESIS. It was one of the first, or possibly the first, decadal prediction systems to be developed back in 2007. And as I'm sure you all know, the aim of these systems was to bridge the gap between seasonal forecasts and climate projections, and seeing if you can get any additional skill in predicting internal variability in the near term by initializing with the current state of the atmosphere and ocean. DEPRESIS 1, it was based on now a very old version of the Hadley Centre GCM, which was HADCM3, which was very coarse resolution. And initially the ensemble was generated by initializing 4 ensemble members 4 times per year with 10-year integrations, and the hindcast period was just 1982 to 2001. In Smith et al. 2007, they showed that when you take the first year of each integration, the model can simulate improved interannual variability when you initialize with the correct initial conditions compared to when you don't, which is shown in the plot on the top. But they also showed that even out to year 9 of the forecasts, you can get an improved root mean square error in the global annual mean temperature in DEPRESIS compared to the control run. That's shown on the bottom plot, where you've got the solid red line shows the DEPRESIS RMSE, and the blue shading shows the range from the uninitialized control. And since that 2007 paper, DEPRESIS has been used to issue the annual global mean temperature forecasts every year since 2008. And these are released on the Met Office website. And the system itself has undergone several upgrades. We're now on DEPRESIS 4, which is based on HADGEM3 GC 3.1 at a much higher horizontal resolution than the original version. It's now initialized just once a year, like many decadal systems, on the 1st of November, with 10 ensemble members, and the hindcast period has been extended back to 1960. Some of the highlights of the results found with DEPRESIS, they include skillful predictions of the North Atlantic tropical cyclone frequency. This was described in Smith et al. 2010. This is for a range of different forecast periods, as shown in the top plot. This shows the skill measured by the correlation coefficient in predicting tropical cyclone numbers from DEPRESIS in red, the uninitialized control in blue, and persistence in green. And you can see DEPRESIS beats the control simulation over every forecast period. And one of the reasons for this is that although there is skill in predicting tropical cyclone numbers in the control run just from the external forcing, in particular the aerosols, as we've seen quite a lot in this workshop, the initialized runs have increased skill in the temperatures in the North Atlantic subpolar gyre. And this is strongly related to temperatures in the main development region of Atlantic hurricane region. So that gives the initialized forecasts an advantage over the uninitialized ones. Next, there was a paper in 2017 by Sheen et al. Showing skill in the summer Sahel rainfall. This was using DEPRESIS 3. In this paper, they looked at 2 different timescales. The first was for the first summer in each of the hindcasts, so that's months 8 to 10. And the second was for the average summer rainfall for years 2 to 5 of the forecasts. They found skill on both timescales, which you can see in the red areas in these maps. These show the correlation coefficient between the observed and the predicted rainfall. And we've also got the time series of the area averaged rainfall on the right, with observations in black, model forecasts in red. But they actually found there were quite different drivers for the skill on these time scales. So for the first summer, the skill is mainly coming from the skill in predicting ENSO, which drives changes in the water circulation, and this affects the rainfall in the Sahel. But on the longer time scales, it's the sea surface temperatures in the North Atlantic and the Mediterranean having more of an influence by increasing the amount of moisture advected into the Sahel from these regions. So those first two examples were about tropical skill, but in terms of mid-latitudes, Dunstan et al. 2016 found that Depressus 3 could skillfully predict the NAO in the second winter of the forecasts, which is months 13 to 15. This is shown by the time series on the top. And they suggested this skill could be related to the ENSO skill at this long lead time. And also at this time, there's also still significant skill in predicting the stratospheric polar vortex strength. So both ENSO and the polar vortex are believed to drive the NAO. But as we've seen quite a bit before, for the extratropical atmospheric skill, the signal from the models was too weak. And at this time scale, it's by about a factor of 2. And more recently, Doug Smith led a paper showing winter NAO skill averaged over longer periods for years 2 to 9 of the forecasts. This was, of course, not just Depressus, it was a big multi-model ensemble from an international collaboration, which I think lots of people here were probably involved with. There was also a similar result found at the same time by Athanasiadis et al. 2020 using the NCAR large ensemble. I think these plots have also been shown before in this workshop, but again, the signal was much too weak, and it increased by to about a factor of 10 on this time scale compared to 2 or 3 on the seasonal time scales. So you need huge ensembles to extract the signal, which they did in the lower plot by lagging the ensemble. And next, more on the interannual predictions, which I guess is more relevant for this workshop. Nick Dunstan did more work looking at the skill in the first 16 months of the forecasts. This was a collaboration with NCAR. They looked at a combined ensemble with Depressus 3 and the NCAR DPLE. And as you can see, they found significant skill for ENSO out to the second year, which has been shown quite a few times before here. But you get increased skill using the combined ensemble compared to using each ensemble on its own. Also, you can see a bit of a difference in the early part of the time series, which is perhaps due to the different initialization methods in these two models. And they also found that this ENSO skill is driving skill in the monsoon rainfall. So for these monsoon regions, which are shown on the plot in the top right. And below, we've got the correlation skill for the summer rainfall in each of these different regions. Here we've got the blue bar showing the skill in the combined ensemble, and the red bar shows the skill if you select only years when there's an active ENSO forecast. And this seems to indicate that the skill is flow dependent. You've got better predictions if you've got an active ENSO. I'll next talk a bit about the WMO lead centre work undertaken by the Met Office. So the Met Office was designated as the WMO lead centre for annual to decadal climate prediction in 2017. And the main responsibilities of this are to collate the decadal forecasts from each contributing centre every year, and then use these forecasts to make the global annual to decadal climate update, which I'll talk about on the next slide. Also to provide verification statistics for the multi-model forecast and for each model individually, and to provide up-to-date information on each of the decadal prediction systems that are used. And all of this is available at the website shown here. So the global annual to decadal climate update, it's basically a report that's issued every spring. It summarises the climate predictions for the next year and the next 5 years based on the decadal forecast provided by each contributing centre. There's quite a big focus on the global mean temperature forecasts, but there's also the forecast anomaly maps, so there's more regional information, and these are for surface temperature, sea level pressure and precipitation, again for 1 year, for year 1 and the years 1 to 5 average. And there's also forecasts of indices such as Nino 3.4 and the Atlantic multi-decadal variability. And it's now considered one of the key annual reports of the WMO, and the accompanying press releases from the WMO and the Met Office so far have had a huge pickup from major international news outlets. So these forecasts are potentially reaching millions of people. The headline results from the last report were that there's a 40% chance that at least 1 year between 2021 and 25 will be 1.5 degrees warmer than pre-industrial levels, but it's very unlikely that the mean of the whole 5-year forecast will be greater than 1.5 degrees. There's also a 90% chance that at least 1 year in the period will be warmer than the current warmest year, which was 2016, which was 1.28 degrees above the pre-industrial. So the next report for 2022 to 26 is being finalised at the moment, and that's due to be released in May. And finally, because this workshop is about societally relevant predictions, I'll briefly describe this product which was developed for the C3S Sectoral Applications of Decadal Predictions project. I think Anca Brookshaw might be mentioning this in her talk as well, so I won't go into too much detail. But it was a collaboration between DWD, CMCC and BSc, and overseen by ECMWF. And each institution partnered with a user in a particular sector to see if we could produce useful predictions on near-term timescales. And I think Andreas Paxian and Bala Solaraju Murali have also got posters on the DWD and BSc case studies in the poster sessions if you want more detail on those. But at the Met Office, we worked with the reinsurance brokers Willis Towers Watson, and they were interested in North Atlantic tropical cyclone forecasts for years 1 to 5, because there's very strong variability on this time scale. And as I showed earlier, this is something that decadal prediction systems are believed to have skill in. So for these forecasts, rather than tracking the cyclones directly in the models, which is often done on seasonal timescales, we just used a relative temperature index predicted by the models. This is known to have a high correlation with observed Atlantic hurricane activity. So it's the temperature in the main hurricane development region minus the temperature over the tropics as a whole. And we did it this way because firstly, tracking is very expensive, and it's also been found that you don't actually gain any extra skill by doing tracking on this time scale, because the skill is mostly coming from the sea surface temperatures in the first place, so you get just as good a result using those directly. So using this multi-model ensemble from the 4 different institutions in the project, we found very high skill, similar to the previous studies, in predicting the basin-wide tropical cyclone activity, which we've measured here by the ACE index. This is shown on the plot on the left. We've got the observed five-year mean ACE in black, and the forecast value, or handcast values in red, and the forecast shown by the bar and whisker plot. And I guess the new bit of work for this project was finding that the models were also able to make a reasonable prediction of the damage caused by the hurricanes. So this is the damage measured in dollars once you've adjusted for inflation and changes in wealth and population. You can, however, see on the damage time series on the right, there are big jumps in the observed losses, and this is when you get a really extreme hurricane such as Andrew or Katrina. This is something that models can't predict, but we've tried to account for this in the probability distributions. So the forecasts for the 2020 to 24 period and 2021 to 25, they've been released on the C3S website, and they're in the form of these 2-page documents. We've got the headline results on the first page. This gives estimates of having above average ACE or above average damages in the next 5 years. And they also show the mean and range of the forecasts. And then on the second page, there's more background on the forecast skill and how they were produced. So to summarise, decadal forecasting has had a long history at the Met Office, but I guess you could say that the shorter forecast periods beyond 1 year have been less explored. So someone's coming in this room. The Lead Centre work is doing a good job of publicising predictions on the annual to multi-year timescale. Developing sector-specific services on these timescales is quite new, but we've got the tropical cyclone forecasts. There are also other products being researched, including rainfall predictions for the Yangtze River Basin in China for lead times of 6 months. And finally, although we know that models do show signals on these longer timescales, as has been mentioned in the discussions, there's still a lot of work to be done on understanding the drivers of predictability so we can have more confidence in the forecast issues. And this links with one of the WCRP lighthouse activities on explaining and predicting Earth system change. Yeah, and that's it. Thank you very much.
Okay, our next speaker is Anca Brookshaw from ECMWF. She'll be speaking also, and I should have said the previous talk was invited. This talk is also invited, sorry. Climate prediction for climate services, current activities and future plans at ECMWF.
Thank you very much. I must start by apologizing for what you will see is a big distance between the abstract that still survives in the program and what I'm going to be talking about. But what I'm going to be talking about is about the activities at ECMWF, including the Copernicus Climate Change Service on multi-year predictions. And I must acknowledge the special contribution, especially in terms of slides from my colleagues named here, including Nick Dunstan from the Met Office, whilst the work is the work of the full team. at ECMWF and beyond. So just to update my promise in the abstract, I will want to tell you about the operational activities on more than a year, more than seasonal timescales. Mention a little bit about research into multi-year predictions, as well as Julie advertised, talk about the climate prediction data for climate services, and in particular, the exploitation of decadal predictions that took place in the last couple of years. So firstly, about ECMWF operational predictions. If you were to go to the website of ECMWF products, which now is open to the public, you will find Nino plumes stretching 13 months into the future. I know I'm stretching a bit the notion of multi-year, but please bear with me. This is something that's been going on for more than 10 years. With the latest version of the operational system, CES5, data has existed since 2017. It is available open to the public. Verification is also now published. There's a number of metrics of verification, which anybody can go and examine all the way back to the first time these forecasts were issued. And this is what you find if you do examine those pages. The initialization periods, initialization months are 4 times a year: February, May, August, and November. The forecast length is 13 months. Real-time forecasts have been created since 2017, and hindcasts at the very least since 1993. The change in baseline to express the Nino indices with respect to some standard WMO climatology is done by post-processing. So here is an example of a forecast from a couple of years ago, which just illustrates a little bit how it does fit observations. In fact, my colleague Tim Stockdale has assembled them all together, and for the start dates of August, here they are from the very beginning of the period. It looks like the hindcast period is in fact run from 1981. The calibration is only done on the more recent 25 years or so. And here you can see the red lines show the forecast, and if you look carefully, you'll see that the end of one red line overlaps the beginning of the next red line by 1 notch, which means 1 month. The black is the observed anomaly. And it's not a bad correspondence. There are some big gaps, some big errors, notably here. 1 year to the next, the forecast did give very bad indications, but in reality, the scores are not very bad. And here you can see one of the skill scores. Unfortunately, this is the nearest I can come to correlation because the diagnostics I showed you earlier do not include the true linear correlation. What we see here is what we've seen already in earlier presentations, that the length into the forecast for which you have skill depends on the start time heavily. This is one thing that will be harder to see by just looking at the DCBP type decadal predictions initialized typically only once a year in November. The bottom line is, though, that the significant values of mean square skill score shown here seem to stretch until about the beginning of the summer following the initial conditions in the second year. So from November, you get about 7 months. From May, you get 12 months, whereas from February and from August, you get, from August, you get 9 months. From February and May, you go into the second year. So you can gain quite a bit of lead time in the predictability. I'm going to move on, and I'll tell you at the end all about what we plan to do next. But now this is the second part of it, which is the research activities into 2-year forecasts. So this was started at the instigation of Antje Weisheimer and Magdalena Balmaceda. They were looking initially at understanding whether the estimates of skill for ENSO in particular, but for other modes, varies depending on the time of initialization. And for this, an effort was made to initialize forecasts throughout the 20th century. There's a couple of experiments, but I'm only going to be talking about that. It was extended later to a 24 months forecast. They're initialized twice a year on the 1st of May and November. The hindcast period covers 110 years. using the coupled model that is in effect system 5. So the IFS cycle at this resolution, it's relatively low resolution than the operations, but and also uses the 1 degree ocean model. What Anca has found, and it's about to publish, I think, in a paper, is that a scale exists beyond 1 year. Here you can see a scale estimated over 30-year periods centered on the dates on the x-axis. And the y-axis, it shows the value of correlation for these 3-month periods into the future. But she also found what she was actually interested in primarily, namely the fact that the carrying of scale into the second year depends on when you started your forecast. If it's in the last 50 years or so, it seems that the second year scale, significant scale is available, whereas early in the 20th century, that is not the case, apart from very early on. So this is something that she finds intriguing, and she's trying to look into the causes of this variation of scale with initialization. She's about to publish a paper, so I'm not going to dwell on this very much. And you will hear in a moment, I think, from Sharmila about some more results from these runs, because these runs have been analyzed in collaboration with the Bureau of Meteorology. Here's a different take from the previous graph, in which the value of the correlation is now shown as a time series with lead time. And indeed, you can see the values of the correlation for the period 1979-2008 is higher throughout the run, pretty much, than that of the earlier periods, higher than persistence in each of these periods. But there are a couple of features in particular. I think she also wants to look at this apparent plateau throughout the winter period of the second year. Very quickly, sorry, we'll move on to the last part, which is the outputs and the work done on the Copernicus Climate Change Service. I've put out here a couple of very basic information about what I'm talking about when I say Copernicus. For those who don't know, not many left by now, I suspect. Copernicus is the European Union's Earth observation program. It operates a number of services, some of which are hosted and operated by ECMWF. In particular, here I'm talking about the Copernicus Climate Change Service, which started in 2015 and is now in its second phase, which started last year. In terms of climate predictions, C3S includes seasonal timescales. This has been from the very beginning a component of the C3S service and has been operational since then. The data is made publicly available for open and free access and use. A decadal prediction service prototype was established in the last 2 or 3 years. The outputs were published in 2021. That hasn't been updated yet. So here I've put the link to the pages where you can find these outputs. Julia very nicely explained one of the case studies. I will have very little difficulty putting you through and describing briefly what else you can find there. But I will say that multi-year predictions are now in our plans for the second period of Copernicus 2 program. Just very briefly, because this will be interesting if you are curious which models we might end up having multi-year predictions from. This is the current setup for seasonal timescale. Everything I'm talking about in terms of multi-year will be a continuation of the current seasonal setup. Probably not with all the models, because a number of the models that you see here, there are 8 components to our multi-system we used for operational seasonal predictions. A number of them are in-kind contributions, so we can hardly push people who give us the forecast for free into doing things we want, and they might not meet with their priorities. But for the European providers, the plan is to try multi-year predictions. Again, I don't want to detail this. If you're interested, I can answer questions, or you can go and find out. The important thing is that data is downloadable. High temporal resolution data is available, which makes it possible to test the application of this data in downstream applications. Tools and computational environment are also available and will be improved in the next few years. So it will be possible to do processing next to the data and make it efficient as well. Lastly, I'm going to show you the full panel of decadal prediction prototypes, case studies, we call them. This is a slide prepared by Nick Dunstan, who led the work package in that particular piece of work on case studies. And very nicely presented the results afterwards. There was a great deal of effort in trying to make their products look uniform as far as possible while retaining the specifics that brought that each of these things brought it to its intended audience. Now, as Julia pointed out, we had a focus on trying to answer real user applications. So the providers, the participants, were asked to come along with a user that they have identified and they could work with. And it was interesting. We learned a lot of lessons by doing these things in parallel. Whilst similar, the approaches were not identical. In some cases, the producer conceded to the user's demands in a literal fashion. People wanted very high resolution data on precipitation on their area of interest. And that is what we attempted, or the developer attempted to do. Whereas in other cases, the user requirement was confronted with the predictability problem and what we know about what can be achieved on those timescales. And the user and producer met somewhere in the middle so as to end up with producing something that's much less precise, likely as not, less appealing to user to a certain extent, but probably more skillful. But you will spot here, if you look just at the headline statements, that all these things look at period means, number of year means. Even if it's for shorter than only a period, it's always at least 3-year mean. And this is something that, as we discussed earlier this week, it's not necessarily what we're looking for here. Likely as not, the reason for this was not that the users wanted this, but because this is where we thought and we knew the skill might be coming from. We wanted to achieve something, so we didn't just concede endlessly to the user requirements. But we did learn a few things, and one of them, I think it's also illustrated by Julia's slide, that we need to understand where the skill might be coming from, even if the user question is quite a long way from that. Because if we don't, we are going to end up doing things that might look good. Machine learning would probably take us there quite easily these days. But the success of the forecast, measured in some average sense over the past period, will be quite flaky. You will need to change your goalposts in order to be able to continue to achieve some level of skill, assuming that, like here, you set some level of skill as a threshold for issuing a forecast in the first place. So I think this idea of understanding where the predictability might come from is becoming valuable, as it does for the longer time scales anyway. As we heard, the WCRP Lighthouse activity stresses the need to do this. This is primarily because in a changing climate, in periods which show for variables that show trends, looking at past performance may not be necessarily a guarantee of anything about the future. My last slide, and by way of conclusions, I rather want to tell you about what we want to do next. So in a couple of years' time, ECMWF's next seasonal forecast system will come into operations. And to continue this history since about 2007 of doing longer than seasonal forecasts, we are going to do it. And we're now scoping the priorities for these longer than seasonal forecasts with C6. I call them longer than seasonal because we haven't decided on the period. We are even considering doing variable periods depending on the start time. In essence, we are looking to see what sources of predictability we might tap into and try to put our resources in the best possible place. We might want to do longer hindcasts over the 20th century, maybe. We might want to do much larger ensembles in a real-time forecast. A survey is being prepared now by my colleagues and will be sent in the next couple of months for response. And I wouldn't be surprised if some of you would not be sent this to pass your opinions to us. The 24-month CES5 forecast I showed you briefly highlights from will result in a paper. Further analysis, I think it still continues at the Bureau of Meteorology. Lastly, C3S will extend the seasonal forecast using most of the system contributing to the service to a period a year or longer, possibly 18 months, 24 months. But we also want to set up some piece of work to further analyze existing decadal prediction runs from the lead center from DCPP to develop prototype of products with users and for users. Thank you.
Okay, our next speaker's in the room. Another invited talk from Emily Becker, University of Miami, on plans for multi-year NMME.
Hi, everybody. I amended my title slightly because plans without any caveat to it makes it sound like we are ready to go, but we are still figuring things out. So this is thoughts about plans, and we'll get to that. So way back in February of 2020, we had a protocol development workshop for extending the NMME. And I'm going to spend a little time talking about what the NMME is. So if you're not completely familiar with it, I will get to it. But this meeting was to draft a protocol to develop an NMME that would extend out to 24 or 36 months. So regular forecasts in a real-time context. We had 4 modeling groups there, all of which are current participants in the NMME. We also had a number of participants, including from the operational side, from potential stakeholders. If you were at that meeting and you're not on this list, my apologies. I had to really excavate my memory because, of course, that was about 20 minutes before the pandemic started. And then this sort of fell by the wayside for a little while. There were some advantages to that, though, because the science has really developed in the last couple of years, as we've seen from the last 2 days. There are a lot more, there's a lot more evidence that this year 2, year 3 interannual timescale is potentially predictable. This was a one day in-person meeting. We had people fly out from California for it. So I'll be interested to see if we fly across the country for one-day meetings again in the future. And I am going to talk a little bit more about the outcomes from this. So the goal of a potential project of extending the NMME is to bridge the gap between the seasonal and decadal multi-model efforts. Currently, the NMME extends out to 12 months. It's a very well-developed infrastructure that has stood the test of time. So the thought is, could we extend this exact same framework that we have out to 36 months and therefore get monthly and seasonal means out to year 3 and near-term annual means? So the averages of months 18 through 30, 19 through 31, so on. If you have this monthly resolution, you can make any sort of time frame that you want. Predictability and potential forecast skill on these timescales, as we've seen over the last couple of days, stems from interannual ENSO variability, reemergence of processes of extratropical oceanic anomalies, land surface memory, sea ice processes, and several others that we've seen over the course of the last 2 days. There is a large array of potential user communities. At this meeting that we had in 2020, we had representatives from the National Ocean Service, from the fisheries, and from the drought community specifically. We were starting with sort of near-in stakeholders before potentially reaching out to like the energy sector or other more distant from NOAA and the US government. Yes, many entities have these longer planning horizons. So hopefully quick overview of the NMME. I could probably talk about the NMME for many hours. So if you want to know more about it or get to sleep, I will happily tell you more about it. NMME was initiated in August of 2011, following a 5-month planning period. That was all that was all the lead time it took to get this going. It was something of a multi-model ensemble of opportunity, I think, to use Hugh Vandendoel's expression. All of these models were fully developed. Many of them already had the necessary hindcasts and the necessary structure to run regularly. And in 2011, we collected all of the US research and operational models. And then in 2012, we were joined by Environment Canada. All of the forecasts are free and available in real time in this case. Most forecasts are made between the 1st and the 6th of the month, and they're released to the public on the 7th of the month. And all of the retrospective data is also available. So NMME has both operational and research components, and they feed back into each other. So it's a very effective research to operations, back to research circle. The real-time images are posted on the CPC website and also the IRI map room. We've had 17 models or versions of models so far, with between 6 and 8 in operation at any time. And we have further upgrades planned this year and then next year even for each of the models. The only model we have that has continued from 2011 is CFS version 2. So that's so the point of that, of course, is to take advantage of model upgrades as they become available instead of waiting a really long time to have a full new system. We have this dynamic as models are developed by their centers. They're added to the NMME and older models are retired. So the question is, does this actually, we assume that this would increase the skill of the forecasts, but actually testing that. So we took 4 different suites out of the NMME. So the oldest one from 2011, and then the approximate operational suite from 2012, 2014, and 2020. Those 4 years were times when there were large changes to the system. So, and then just compared their performance over the common hindcast period. It would be nice to be able to verify if we got a more successful real-time forecast, but that's extremely complicated and we don't have overlapping times for all of those. So just to put them all in the equal playing field, taking a look at their their hindcast performance. These are very coarse metrics. It's the area aggregate pattern correlation for precip at lead 1 and for temperature at lead 1. And these are seasonal, so it's the January forecast for February, March average. And the purple line is the newest suite and the light blue line is the oldest. So we see with precip, unfortunately, we have actually not made a lot of progress in this. There had been, I think, about a 3% improvement. And if you're looking at that and saying, wow, that's a really high anomaly correlation for precip, this is global precip, so almost all the skill is from the tropics, where in fact there is a pretty high predictability for precip. But for temperature, on the other hand, we've seen about a 30% increase in this anomaly correlation. A lot of the older models had a less faithful representation of the trend, but that's not the only source. Some of the newer models are better at reproducing a temperature variability. And then if we look at sea surface temperature, there's some interesting things here. We have in fact seen a pretty solid improvement in the global sea surface temperature. Again, a lot of the skill comes from the tropics, but that is important as well. So these maps I'm showing, if you just look at the bottom one, it's the difference between the oldest suite and the newest suite. And blue is higher anomaly correlation. So the fact that the map is mostly blue is a good indication, but also it shows you where we're seeing these improvements. So we haven't necessarily made a lot of improvement in the ENSO region, but it was very, very high to start with. But in fact, we have seen pretty decent improvement there. And then at the lead 5, we've seen a large overall improvement, but in fact, if you look at the ENSO region, it's red, which means we've actually seen a decrease in the hindcast skill of predicting ENSO at a longer lead. So this is the lead 5 forecast out into the future. And why is this? This whole long story has a point. I'm coming back to what Jerry actually kicked us off with. One thing about what he said is this this drift in the climate. And in fact, we find this is an excerpt of a figure from a paper that Michel Leroux did looking at the trend in this region, the representation of the trend. And we find it a shorter month, the trend, this is model trend minus observed trend. So we find at the shortest lead, the model trend is a little bit stronger than the observed trend for most of the models. But at the longest lead, which she looked at, which is this 8.5-month lead, we find that this trend is much stronger. So this could potentially be one of the reasons leading to that decrease in longer lead skill. But the reason that I'm bringing this up is because we have, hopefully this is my next slide. Yes, lessons learned. If you have looked very, very closely at a system every month for the last 11 years, you start to notice patterns and trends and things that maybe if you were to debut a new system, you would really want to be aware of, especially its impact on a long-term forecast. So if this trend problem extends, which it probably very likely does, and increases with the length of the forecast lead, then we really need to be aware of that. Another area that we've noticed this in is the prediction of colder than average surface temperatures in North America. The trend is actually quite strong. And since seasonal forecasts are an anomaly relative to a fixed climatology, and that climatology is only updated every 10 years. For example, by the time we got to 2019, relative to a 1981 to 2010 climatology, almost every forecast was for above average. And there was information to be had from those, but from a user perspective, those required a lot of interpretation. So anyway, that's just one lesson that we learned sort of on the more physical side. And then when it comes to actually running an operational system, the most important thing, I tried to put it in larger font, but then PowerPoint made it small again, but is a well-vetted protocol. The protocol being the guidelines to which each modeling center needs to adhere to produce their models, and less so about the consolidation of the models into a multi-model ensemble. The protocol really pertains to the models as they are produced by the modeling centers and delivered to the overall system. So I have a draft protocol later that I'll get into. Ease of data availability and visibility is key. We had several different databases over which various components of the NMME were distributed. The one that got the most use, perhaps unsurprisingly, is the one that has the most straightforward interface and the most user support and all that. So this, it sounds like an obvious observation, but it is in fact extremely important and needs to be thought of ahead of time rather than as an afterthought. Resources are necessary for maintenance. You can't just get started and then hope that the system will continue without too many problems, without additional and continuing resources for maintenance. It's also key to have training, documentation, and basic scripts available. For SubX, which is a similar multi-model ensemble system, but for the sub-seasonal timescale, so out to 45 days, Kathy Pajon made a whole bunch of basic scripts available on her GitHub, and those have really helped the user community to obtain the data and do basic analysis functions on it. So those are very good. NMME is catching up on that. In fact, it was not something that we started out with. And then regular research and operational discussions. We have a NMME monthly telecon. I think many of you have called into this in the past. And I'm amazed that each month we still find something to talk about and have a good discussion, and there's so much ongoing research. So this has, we talk about the operational issues for a few minutes in the beginning, and then we will have a research discussion and then an open discussion at the end. So any program that we were to go into, we would want to have this kind of regular check-in. So now I'm going to get into the more protocol development here. This is a bunch of word slides. I'm not used to giving talks that are all word slides, but I'll try to make it a little bit energetic here. So what's distinct from existing decadal prediction efforts, critical issues, and then draft protocol considerations. So this is sort of the second half here. So just a few differences here between the existing programs such as CMIP6 decadal climate prediction program and the proposed multi-year prediction, multi-year interannual. Whenever I say multi-year in this case, it's this resolution, monthly resolution out to 36 months. So they're both multi-model systems. CMIP6 DCPP has an emphasis on the annual mean or several years average. Oh, is that my, 2 minutes? Is that my, okay. Oh, did I miss the 5? Oh, all right. Anyway, I'm getting there. Okay, so we know all most of this anyway, so I'll go ahead here. All right, but just a couple of important considerations. Matt and I were talking about being long talkers, but anyway, you learn from the best. All right, data storage and management, very important issues. The database host must have adequate space. Seems trivial, but we need to plan ahead. These are large databases and an accessible interface. The virtual map room, very important, so that users can visualize the data without having to download it, process it themselves, and make their own maps. And then the raw data will be made available. This is a daily and monthly resolutions. Daily data will have a few, there'll be fewer of those available, but there is a demand for this daily resolution. And then the initialization frequency and timing. It needs to be initialized frequently enough to provide predictions for varying periods. And then at this protocol workshop, we estimated that 4 initializations per year would provide the temporal resolution necessary. If we could get to 6 or 12, I'm sure there would be uses for those, but it's a balance between practical and practical and the desired. So research priorities and project assessment. Research priorities should be developed ahead of time. And then, of course, as happened with NMME, we had some research priorities developed in 2011, but over the last decade, there have been 600 papers published using NMME to show different, seasonal research. And then ongoing performance assessments are important. So here's my draft protocol for the, our draft protocol from the 2020 workshop. And referring back to that workshop, if you have, if I've said something that doesn't jive with your memory, please just let me know, because as I said, it was a long time ago, somewhere between 200 and 400 years, I think. Let me know if there's something that I didn't cover that you think was critical from that. Okay. The details of this aren't necessarily critical to go over right now, but I think if we have a discussion later, we can refer back to this. All right.
Our next speaker is, I hope I'm pronouncing your name right, Birgit Manning. That's right, from DWD, and she'll be speaking user-tailored representation of climate predictions, the DWD climate prediction website.
Hello, and thank you for the opportunity to talk here. As mentioned, I'm from the Deutscher Wetterdienst, the German Weather Service, and I'd like to present to you our user-tailored climate predictions website. It is a website made for our users and also kind of with our users. It was really a co-design, and a lot of user feedback still goes into the website. Actually, a lot of things I'm saying will seem familiar to you from Carly's talk yesterday and also from the summaries you heard earlier today. So we set up this website because we have we registered a lot of interest from different users, and typically those users have no background in climate sciences. So we wanted to give them an easy access to a sometimes quite complex information. on climate predictions. So who are our users? They are from all kind of different sectors. I think our closest users with whom we work closest together are from the forestry sector, but we also have users from water boards, from water and shipping authorities, and also from the humanitarian sector or, for example, fire department. We have users who are already using or plan to use our data themselves, and a lot of users who only look at our end results. So DWD works towards a seamless prediction approach over all timescales, and for us, this means climate prediction on all 3 timescales. So this is actually a screenshot from our website. We started with decadal predictions in 2020, where we look at year 1 and lead years 1 to 5, 3 to 7, and 6 to 10. Last year, we integrated our seasonal predictions on the website, where we look at 3 month means. And you can see this is a work in progress, but probably later this year, the sub-seasonal predictions will follow. And the principle is that the graphical display of all 3 timescales is consistent, so that the user can very easily understand information from the different timescales. We show our information on 2 layers of complexity. For one thing, we have the really basic climate prediction. There we try to reduce the complexity of the climate predictions to a rather simplistic graph, but therefore it's easily understandable. And we only do this for Germany because obviously our users are typically from Germany. We also provide expert climate predictions. These show a bit more details. And also on our website is a heap of background information as we explain literally everything we do, and we try to be very transparent in what we do and why we do it. We show graphs for 3 different regions. One's a global scale, and then we kind of zoom in to Europe, where we have a bit of a higher resolution. And most important for our users is the German scale, where we apply empirical statistical downscaling to achieve this high resolution of 20 kilometers. I put some more information of this in the appendix if you're interested. And our downscaling preserves the skill from the global climate model, but it does not improve the skill. So it's really just to get high resolution data at the same skill level. And additionally, for our basic climate predictions only, we show aggregated area means for 4 German regions. The types of visualizations we provide are maps on the one hand for all regions. We have time series, which show the time series for the area means. And for basic climate predictions only, we have all information which you can find in the time series in these nifty tables summarized. And the variables at the moment, we show information for temperature and precipitation, but there are more to come. We are working on this. We show both ensemble mean and also probabilistic predictions. And our principle is to always show the prediction in combination with its skill. So this is a graph from our expert climate prediction, and you will see the prediction value itself through the color shading of the dots you see. And the skill of the prediction is shown by the dot size. So here on global scale, 5-degree resolution, temperature, decadal prediction, we have a rather high skill. So also nearly all the dots are large, but this will look different for precipitation, for example. And for our basic climate predictions, we show the skill in the form of these shiny traffic lights. And red means no skill. And yellow means we are comparable to the observed climate mean or our reference prediction. And green means we have skill. So we determine the skill through the mean squared error skill score for the ensemble mean prediction and through the rank probability skill score for the probabilistic prediction. And our reference predictions are typically the observed climate mean, but for our expert prediction and the decadal predictions, we also use climate projections as a reference prediction. Our expert climate prediction section has a subsection for our skill, where we show maps for MSESS, RPSS, and also for the correlation. Then as an information, we use a statistical post-processing on decadal predictions, and the recalibration was developed by Pasternak et al. And this improves the skill also. So let's take a closer look. Our basic climate predictions, which you see here, they are really rather simplistic, which means they can also be kind of boring, but this is what our users wanted. Here you see a probabilistic prediction of temperature, and we use terciles. This was discussed before here. So, and the traffic light means that we have skill. So here it is that the RPSS is above 0 and it is significant. Also from our basic climate prediction, the same thing as a time series. And here you get a bit more information about the distribution of the ensemble members through the 3 categories. Here you see the same information from before, from the time series, summarized in this table. Here are some examples from our expert climate prediction. The example here is ensemble mean prediction for precipitation over Europe, and you also see that over Central Europe, unfortunately, we don't have any skill. This is the probabilistic prediction for precipitation, and here you get a bit more information than for the basic climate predictions through the shading, which shows how many % of the ensemble members are within this category. And this is an example for a time series of ensemble mean predictions, 1-year means and 5-year means. The dots are the prediction itself, and the box whiskers are the spread of the ensemble member, whereas the gray shading is the spread of the observations. And here is an example from our skill category, a map for temperature correlation. Again, color indicates the correlation value itself, and the dots signify whether it's significant or not. Our future plans, these include, as mentioned, the sub-seasonal predictions. We are pre-operational with that for that. We also plan to do multi-year seasonal means. Also, a colleague of mine is working on a seamless time series where we will try to contextualize the climate predictions between observations in the past and climate projections for the future. And this is not the final form of what we will publish, but it's an intermediate result. And also, because user demand is really high on this, we will add further variables. Next step will be drought indices and also predictions for ENSO. We plan for our next decadal predictions, which will be published in 2023, next year, that we will use an updated model version, which will also include a new set of hindcasts. And we are really excited to use or plan to use multi-model ensembles. And very important, everything we will do will be in feedback loops with our users, especially how we implement it in the end on our website. So user engagement is really important for us. So as a summary, we have a high demand for climate predictions on all 3 timescales, and the users are really manifold from very different sectors and from business, politics, and society. Also, our website right now provides information on climate predictions, and the information is consistent on all 3 timescales. And everything is developed in very close collaboration with our users. And we do this via workshops and also via close personal interactions. And what we try to do is to meet our users' needs. As mentioned in some talks before, this is not always possible, but we do what we can. And we also try to enhance their understanding of climate predictions, because we realized that they often have problems with understanding of the probability predictions. And also we try to create awareness for the importance of the prediction skill, because this is not always the case. And as you all know, this is the most important thing. And I can only say this is a work in progress. There will be many more things to come. And we are excited for everything that will be and will come. Sorry. Thank you for your attention.
Okay, our last talk before the discussion is from Sharmila Sur from the University of Southern Queensland, Bureau of Meteorology, and she'll be speaking on towards development multi-year climate prediction framework for Australia.
So thanks for this opportunity. So this work, in this work, I'll discuss some of the aspects of our ongoing research on developing multi-year prediction framework for Australia as part of Northern Australia Climate Program. So, and I also like to acknowledge my collaborators from the Bureau of Meteorology and also from the ECMWF. And the ECMWF team has provided their latest experimental 20th century hindcast for the assessment, which I will show in later slides. Yeah. Can you see my second slide? Yeah. Okay. So the main motivation is you can see from this the plot the rainfall variation over Northern Australia. As you see that Australia experiences drought and flood-like conditions at a multi-year timescale that have profound impact on the climate-sensitive sectors, including agriculture. And the Northern Australia Climate Program actually aims to improve the understanding of multi-year variations, and also wants to assess the feasibility and the potential predictability for multi-year climate forecast, with especially a focus on the Northern Australia, and that will feed into the development of multi-year climate prediction framework for the Australia. And as we mentioned, that the drought is one of the biggest challenges that graziers face, and which has a significant impact on the agricultural outcome and also the productivity. So the Northern Australia Climate Program is trying to provide them a better, better inform them to better manage their productivity. The other motivation of this work is to have a long-range ENSO predictions, as we know that the ENSO has a significant impact on the regional Australia via atmospheric teleconnections. ENSO events that last for 2 or more years, the multi-year El Nino events, they have more severe socioeconomic impact. And therefore, there is a growing demand for long-range ENSO prediction and the multi-year climate information in Australia. And therefore, the skillful prediction of ENSO and its related impact beyond 1 year will be very crucial for effective risk management. And we see from the previous studies and also from the other talks in this workshop that that indicates that there is a predictive skill of ENSO well beyond the typical 2 to 3 seasons lead time used by most of the operational centers. And for example, the Bureau provides around 6-month climate outlook. And therefore, and we also see that the efforts on the quantifying this ENSO prediction skill beyond 1 year is still very limited, partly because of the lack of long records of seasonal hindcast. So therefore, in this study, we try to understand the basic science, try to improve our basic science of the multi-year wet dry conditions over Northern Australia, and whether we can predict those conditions. So first start with the recent paper that we published, where we looked at the main climate drivers of multi-year wet and dry conditions over Northern Australia. And we identified that there is a regional asymmetry between the northwest and northeast of Australia. We further identified the mechanism which leads to which drives multi-year wet and dry conditions for northwest and northeast, and particularly for the northwest, we find that there is a dominant role of the local feedback mechanism between rainfall, wind, evaporation, combined with the soil moisture memory that modulate the multi-year climate, multi-year wet and dry conditions over the west part. And for the east part, we found that there is a dominant role of ENSO, low frequency ENSO, that drives the multi-year droughts in that particular region, which are published in the scientific report. Next, we looked at the assessment of the ENSO predictability, as we see that the ENSO has a very important role for the west part of Australia. So to begin with, we did some assessment using this experimental multi-year hindcast. We start with the previous assessment using the DePrecis 3, but with a limited ensemble of 10 members and 25 start dates, where we found that the ENSO scale varies with the hindcast period. We further try to run the Access S2, which share the same DC2 model as DePrecis 3, and we found, and we did it for just for a 6-member run, and we found that still with the limited ensemble, the model could predict ENSO 1 year in advance with the May start. But those two, with this two limited ensemble, it was really difficult to address some of the different aspects of ENSO variability, ENSO predictability, because of the short hindcast period. So the latest the hindcast from the ECMWF, which has a 20th century hindcast of 22-year long hindcast, which gave us the opportunity to to address various aspects of ENSO predictability, because of having a good number of samples of ENSO events and transitions and other things. And it can also give us opportunity to assess the prospect of having 2-year climate predictions. And today, before my talk, Anca has already briefly mentioned about this hindcast. So I will not go into the details of the hindcast, which you can find it after the talk. So we mainly use this hindcast to address some of the fundamental questions related to ENSO predictability, and we also tried to see the prospect of having 2-year climate prediction. So first start with the long lead ENSO prediction, whether there is a predictability beyond a year. So how far we can predict and so after 1 year. So we checked 2 start dates. Now the top one is for the November start date, and the bottom is for the May start. And we selected 3 different hindcast period. The first one, the green, is for the total 110 years of data. The second blue is the recent 50, and the red one is the recent 30. And as you see from these 2 plots, that the ENSO can be skillfully predicted up to 1.5 years in advance when we use the November starts. But for the May start, the ENSO can be predicted just 1 year in advance. And we also see that the scale largely depends on the hindcast period. And initially we found that we thought that the best forecast are achieved in the recent period, but actually that is not the real case. There is another work from Anca from ECMWF, and she showed that there is a strong decadal variation in ENSO prediction skill, which also affects the total ENSO prediction. Next, we try to address which ENSO phase is more predictable. Is El Nino is more predictable than La Nina, or vice versa? And here I show some of the results based on the subset of El Nino to La Nina transition and La Nina to El Nino transition based on the ensemble mean forecast. So as you see from these two figures, that the El Nino to La Nina transition is more predictable in this model compared to La Nina to El Nino. And therefore, it means that the development of La Nina in the second year will be more predictable than the development of El Nino in the second year. Next, we also try to assess the prediction skill for the multi-year ENSO events. Here I show the one-year El Nino event and back-to-back El Nino events from the model compared to the observations. And as you see that the model can very well reproduce the one-year event. And for the two-year event, the model can predict whether this current El Nino will terminate into the following year or it will continue, but it actually underestimates the magnitude. But actually, the promising thing is that the model could predict the duration of the multi-year El Nino. That is quite important. And we also checked the physical processes that control the predictability of ENSO duration for one-year event and two-year event. Here I show the composite evolution of SST, surface temperature, surface wind, and in the equatorial Pacific region. And you can see that the model can predict the distinct evolution of these variables, particularly for the single year event and the multi-year event, though it underestimates the magnitude. We also looked at the two-year climate prediction for the global SST, particularly for the northern wet season from November to April. And here I show the two-year prediction starting from the November start date for the year one, and also for year two for both November and May start dates. And we can clearly see that the two-year prediction of wet season global SST anomaly is quite skillful. Most of the oceans, especially in the equatorial Pacific region. We further checked with detrending the hindcast, and we see that the prediction skill, the good prediction skill that we see in the Northern Atlantic and over the Indian Ocean, that reduced when we remove the trend. So therefore, the warming trend in the tropical Indian Ocean and the North Atlantic also contributed to the overall good scale, and which signifies the role of this the model trend on the multi-year performance of the multi-year climate predictions. And lastly, I show the two-year prediction of regional rainfall over Australia. So the first figure is for the year one, for the averaged over the northern wet season. The second is for the year two, and the third one is the average of year one and year two. And you can clearly see that there is a skillful prediction of wet season rainfall for year one and also for the year one to average, especially in the Eastern Australia, which is basically reflected from the good prediction of ENSO for year one and year two. And but we still see that that there are some challenges which can be which is evident from the scale of year two, where we see that there is a limited scale in predicting the year two rainfall. So we are trying to have more investigations to understand the model biases and also the process-oriented understanding of the climate predictability. And that will give us opportunity to achieve a greater confidence about having a future real-time operational forecast. And so finally, the summary is what we learned from this Northern Australia Climate Program, that we have now improved basic science of multi-year droughts, and we have provided improved industry and community knowledge on the drivers of multi-year climate variability over Northern Australia. We also now have a better understanding on the ENSO predictability beyond a year. We see that we can achieve ENSO scale beyond a year, even beyond 18 months in advance. And we also see there's some promising predictability of multi-year ENSO event, which signifies the prospects of having extending the seasonal operational forecast beyond a year, and which actually derived strategy from the Bureau of Meteorology, and they have decided to have a future strategy for extending operational ENSO outlook up to 2 years into the future. And for that, the Bureau has started doing 2-year experimental hindcasts from Access S2, which are currently underway, and we will be doing more further assessment based on those hindcasts. And finally, all the results that we show is important for development of a multi-year climate prediction forecast framework. And we see that we can have a skillful 2-year prediction of global and regional climate with some limitations, but both will be very valuable for managing droughts, climate risk, and decision making across Australia. So the main key point is that the skillful prediction of ENSO beyond a year provides a new foundation for predicting droughts and flooding at multi-year timescale, and which will be our new future. So I have listed some of the published and papers, and some which are in pipeline, and I'll be very happy to take any questions. Thank you.
Okay, we have a little time, not just by the light, for questions. We'll start with one online. Could you pass that to Emily? From Adam. Adam, did you want to jump out and ask a question?
Sure, yeah. I just need to work out which one. I posted a couple. Matt, which one are you looking at?
You can read it if you want.
Which question were you looking at, Matt?
Is the increase in skill between different versions of the NMME
Oh, yeah.
also partly explainable by increased ensemble size and later NMME sets? We find that skill increases substantially with ensemble size, especially in the extratropics.
Yeah, very interesting question. As it turns out, between first and second NMME suites, we went from 7 models to 6 models and actually decreased the ensemble size in that case. Not substantially, I think from maybe 75 to 65 or something. And in fact, saw a large increase in skill. So the number of ensemble members has fluctuated between currently real time, we're at about 110. But it's fluctuated within enough, a small enough range that I don't think that's accounting for it.
We find, Emily, that in order to see, a kind of fair difference between different versions of our systems, that we have to plot the skill as a function of ensemble size, and then you get a kind of curve that climbs with ensemble size, but hopefully the later one climbs faster with ensemble size, if you see what I mean. So we look at it like that. That can help to sort of standardize for the ensemble size and remove the effect of changes in ensemble size. Might be worth a go.
That's a great idea. That's a great idea. Matt will probably kill me if I talk too much, but also one of our theories is that the model diversity improved when we included the models from Canada. Actually, they were more different from the other models we had before.
Yeah, it'd be good to try and separate the effects of the different models from the ensemble size, I guess. Yeah, thanks.
So I have a question to all the speakers who have discussed multi-year prediction of ENSO. the question is the spring barrier for ENSO prediction no longer a showstopper for the multi-year ENSO prediction?
Anybody who wants to, any of the speakers who wants to answer?
I can have a go if you want.
Yeah, just go for it.
I think what the results that we saw in our diagnostics for the operational system show that there is a problem with some kind of spring barrier. It kills dead the skill in the second year, but depending on how far away from the first year's spring predictability barrier you initialize, you might be able to go over the first. You're not going over the second. That's what those variable length of significant values of skill that I showed indicate, I thought.
Any of the other speakers wanted to answer that?
If I could add to that, I think the results that Nick Dunstan found, there is a really big decrease from about close to 1 to 0.5 in the ensemble he looked at. So it's still significant, but I'm not sure if that decrease to 0.5 is then making your forecasts a lot less useful out to the longer, well, once you've gone past the barrier.
Okay, we have a question online from Martha Buckley. Martha, if you wanted to ask.
Yeah, my question was for Julia, but actually I think others might be want to chime in as well. It's just a question about the decadal, like using 5-year averages versus the 1-year forecast. So Julia showed that I think for hurricanes and Sahel rainfall, the 1 to 5 year forecast was more skillful than the year 1 forecast. And presumably that's just because you're averaging over some unpredictable variability when you do that 5-year average. But I'm curious, like, if you just looked at the variance, like on the 1-year time scale versus the like 5-year average variance, how much more variance is on the yearly time scales? Because that would kind of tell you like how useful, like how much of the variance could be predictable, in these skillful 5-year mean forecasts, right? So, is it useful information essentially that would tell you? So I'm curious about what the variance ratios are, if you know.
I think I'm not sure what they are exactly, but for the 2 case studies for the Sahel rainfall and the tropical cyclones, there is still very large variability on the 5-year time scale. So for the Sahel, I think it's mainly driven by the really dry period in the 80s. So I think these systems are showing they have some ability to predict a prolonged dry period like that. So it could still be a really useful thing. And similarly for the hurricanes in the 70s and 80s, there was a noticeable lull in those periods, which is when we worked with Willis on the insurance case study, they were still interested in a 5-year mean, and I think the insurance industry had done quite a lot of work on predicting 5-year means, but just using statistical and climate models before.
Thanks.
Question from Jerry in the room.
Yeah, this is for Julia. I was interested in your hurricane prediction activity, but one of the systematic errors in a lot of our system models is that a lot of times the tropical Atlantic SST gradient actually goes in the wrong direction, and you tend to get cooler than observed SSTs in the main development region as a consequence, which then contributes to fewer simulated hurricanes, even at high res in coupled Earth system models. So I was just curious how you were were you rescaling your predictions based on that systematic error? How are you taking that into account? Because you showed some really good skill for predicting or inferring hurricane activity from predicting SSTs in the main development region. I was curious how you handled that.
I guess we're doing it's a relative temperature index that we're doing. So main development region minus the whole the tropics as a whole. Also, we implicitly bias correct the sea surface temperatures because we use just a linear regression of the past observed ACE index or the damages onto the model forecast temperatures. So we go directly from the model values to the observations, so that can implicitly get rid of any biases that you've got in the sea surface temperatures.
Okay, thanks.
Anca, you had a question?
I had an answer, I think, to Adam. I tried to type it, but my typing skills have gone downhill severely. I was saying that we do have 7-8 models now. We use 7 of them, and we tried to compare the scale of the 3-model ensemble with a 5-model, with a 3-model multi-model, 5-model multi-model, and a full 7-model multi-model, and we couldn't see any differences in scale over Europe. The bigger differences were between the multi-models, so some diversity thrown in, and the individual components, but not between the multi-models just by adding ensemble numbers. Again, it's just a test of opportunity, but I think it goes a bit in the direction he was asking.
Robert, you'll have you take the last question.
I had a question for Emily about the resolutions in the NMME. So wondering what's the typical resolution for the NMME, how it's changed over time, and if there's any resolution requirements as part of the protocol.
The native resolution of the models varies, and that's left up to the modeling centers as that's part of the protocol, but the resolution that the data must be delivered in is a 1-by-1 horizontal resolution, and that has not changed. And in designing a protocol for a new, for a multi-model or multi-year NMME, we could consider a higher resolution, but that's really a very flexible and available format for people. So it hasn't changed, to answer your question, in 11 years.
Oh, did you? Okay, I have a different mic. Actually, although it's occurring to me, I'm going to need somebody to run around with that mic, maybe. We are nearing the end, and I appreciate everybody sticking around till the end. We wanted to kind of see if we could summarize maybe a couple of key directions that we could go, a couple of recommendations we might make. Obviously, the SOC is going to get together later and work on a workshop report, but this is a really good opportunity for you to tell us what we should be saying, especially to funding agencies. Oh, that's right, I guess. Okay. So as we've heard certainly today, and as Emily had discussed, this idea of trying to do a multi-model ensemble of multi-year forecasts has been kicking around for a while, and obviously a number of the different operational centers are doing various aspects of this. Either they're planning to do it, or they have already started. And so one of the things that we've been thinking about is then what are the kind of the key aspects of an effort like that. So that font looks kind of small there. I'll just kind of read it to you. So the questions here is we have this opportunity to come back and to try to develop the multi-model ensembles, not just to extend the time range, but also to maybe rethink the nature of the kind of variables that we'd like to save. So for example, we want obviously to extend to a longer lead time. How far do we want to go? We kind of thought 2 years ago, 36 months seemed to be a reasonable length, certainly kind of a minimum requirement. The question is again, as will be always the case here, resource issue. Is that long enough? Is that too long? Maybe that's a waste. Maybe you do a little larger ensemble and you don't go out as far as 36 months, or maybe you want to go longer. How often do we run this a year? 12 times a year, just 4 or once? One thing we found with some of the model analog hindcasts that was shown in Jaile's poster is that there's a very strong seasonality to this multi-year prediction, and to capture that might really require a fairly frequent initialization. So I at least would tend to argue a minimum of 4 times a year, but I'm greedy, so I would like to see 12. But that's kind of a question. We clearly need more ocean variables, particularly including BGC. It's pretty clear that that's a potential forecast target. So there's a question about how to do that. But of course, not all models are equipped to output BGC variables. So then, you know, what kind of variables? Sorry?
So let me just chime in here on the BGC part, Matt. Also, I think we should recognize the potential issue here of most of these forecasts that are being done prescribe CO2 in the atmosphere, so the air-sea fluxes of CO2 are somewhat in doubt here, and how useful they are. So there needs to be some thought about exactly what's the right way to entrain the BGC community in how we do these forecasts.
Yeah. I mean, I think that's essential. I mean, that's going to be the point we'll hit to also, is that we have to worry about how the users, what they want. I think here, what I was trying to get at was that the variables that we need, we're not necessarily going to be outputting BGC variables out of the hindcast, but what forecast variables would be useful for the community in just this way to ask whether they can make a prediction that would be useful out of it. And this is also true for the coastal prediction community for the same sort of reason. There's issues about whether you want to have things like bottom temperature coming out of these models out of the coast to the extent that they predict it. That can be useful for fisheries. And similarly, there's questions about land variables. Again, what land variables should we be outputting? How long should we be doing the hindcast period? Do we want to start in the early 90s? Do we need to go back longer than that? What are the impacts of the different initialization strategies, which might be an advantage of having a multi-model ensemble, because potentially we'll just have different initialization strategies as part of the different models. But maybe we also want to test it within a model. That's another question. And then what I think maybe I could have put up a little higher is unlike what's been done in the past, do we want to integrate the users directly into the initial planning? So that will help us considerably in terms of thinking what kind of quantities we want to be saving. There's certainly always been requests, I'm sure Emily's gotten sick of, requests from different user communities. Do you have this? Do you have that? Do you have that? And we're sorry, but they weren't made available to us. And so there was nothing we can do. And so getting that kind of information up front is going to be important, but obviously we can't survey an entire universe of user communities. So how we do that is also an important question. And then ultimately, who's going to pay for this? Who's going to fund it, especially considering Emily's lessons learned? It's clear there's resources needed just for basic maintenance, which is the boring thing that nobody likes to spend money on, and storage and distribution. What level of interface do we want? We saw, obviously, for example, DWD has a very nice interface for their forecasts. You know, is this, we want something along these lines, or how do we do that? And how are we going to coordinate this with international efforts? You know, do we want to come up with a certain protocol? Do we just want to have a meeting and say, well, our goal in the U.S. and North America is to do this. What are your interests? You know, again, these are open questions. So this is just my list. I'm just kind of open it up to see what people think and if they have other suggestions or comments. I think there's mics around there somewhere. Online as well, obviously. Sorry? Anca? Yeah, Anca.
It's probably, sorry, it's probably a rather obvious suggestion, but I think we need to organize ourselves to consult on internationally on these technical matters. This meeting has been excellent in understanding the reasons why people might think this is doable or they've done it already, but how they've set up the practical arrangements hasn't been much attacked here. And it's probably a boring technical detail. I know it is for us. But for example, I've heard of some very intricate yet ingenious plans by the Bureau of Meteorology about how to initialize, how large a hindcast, how many times, how you optimize the effort versus the value. Because it's all very well to say, oh, we'd like to have this, we'd like to have 100-member ensembles, but the costs kill you very soon. So understanding where best to put the limited resources, and I speak here from somebody, from the point of view of somebody who's usually approached for funding as opposed to the other way around. So, so I think learning from each other's experiences and compromises and shortcomings, given the compromises, would be valuable.
Adam? Or Andy and Adam.
Oh yeah, I was just going to say to your point about integrating users into initial planning of hindcasts. It occurs to me that's a pretty good idea. In certain respects, it's not just asking for certain types of variables. And we did hear from one presenter about how it's always this balance of providing what's scientifically justified versus what users may think they really want or do really want. But another issue is just even the initialization timing. You know, for instance, there's a lot of big decisions that get made right around April 1 through April 5. And so if you make one of your initializations on April 1, the data is not available until mid-April, that forecast won't be used as optimally as it could otherwise. So if you made it in mid-March, it could be ready to go into the planning processes of certain users. So that's just one example, but I think there's a lot of argument for having that kind of perspective included early on.
Okay, Adam?
I just had a question. Maybe it's for you, Matt, or others there. I'm not sure. About the multiple start dates per year. For the longer range, beyond seasonal, we've always, just run, say, from 1st of November. That gives you a free seasonal forecast for the next winter, if you like, and then we go out to 5 or 10 years. We haven't done a lot of work, I must say, on looking at different start dates, although we have run interannual forecasts from a May start. But my impression is, and I'm sure must have missed the evidence, because my impression is that actually the skill is not that sensitive to the time of year when you start the forecast. Rather, what we see when we plot skill as a function of lead time is that it's sensitive to the time of year when you do that. So for example, for ENSO is a really nice example where if you start in month 6, then you get good skill in month 6, but lead time 6 because you're in the winter. If you start in January, you'll get good skill 11 months later. So it looks like it's different and dependent on start date, but actually it's mainly just because it's the boreal winter season that shows the highest prediction skill because of the ENSO peaking in variability then. So is there more to it than that, Matt, or am I being too simplistic?
No, I mean, I think there's a lot of truth to that. And we certainly see that for the 2-year ENSO skill. It's very strongly tied to the verification time. But I think that kind of interacts also with what Andy was saying, that it's worth thinking then a little bit about targeting certain times. Basically, it's not so much the initialization time maybe that matters, it's the verification time. But you'll be doing that at different leads. So obviously, if you're trying to verify, in December, you could run once a year, and then you'd have, if you initialize in November, you'll have a 1-month forecast and a 13-month forecast, and maybe nothing in between.
Yeah, I agree. Yeah. In fact, we've seen the skill actually that doesn't decline monotonically, right? Sometimes it comes back up, doesn't it, in the second winter? Yeah.
Yeah, in fact, this is kind of in response to what Tony was saying. What's striking to us is precisely that, that it's, people sometimes call it more of a persistence barrier maybe than a predictability barrier, because you have a lot more noise at a certain time of year, but then the noise, as it goes down, the signal basically is back in the following year. But that's very tied to the seasonal cycle. All right, anybody else in the room? Or was there anyone online? Is everybody good with this? Yeah, Robert. Can you get him, Robert? Oh, you have one. Okay.
I already have one. So given that there's a lot of resource trade-offs here between how long you forecast, how many times per year, ensemble size, resolution, just think it's worth paying attention to some of the statistical methods that have been advanced to reduce the number of reduce the ensemble size you need, both linear methods and nonlinear machine learning based methods that can identify signals more efficiently. Then you maybe don't need as large of ensemble size. You can increase resolution. You can run longer simulations, etc. And so, one thing that could be considered in this trade-off.
All right. We're getting to the tailing end of a workshop. We haven't gotten yet to the. Do you have a question?
Actually, I just wanted to advocate also for more ocean variables. It's already there, but I think that would be very important, both for having quantities that we can use for applications, but also I think these outputs, like from the outputs from the NMME or other similar systems, I think can also be used for understanding. I mean, I think the skill that you get is an important key for trying to figure out how the system works and what. So I think there can be also various uses.
I just wanted to add to the comment on that first bullet, what longer lead time and how many times a year, building on what Andy said. There's also a lot of natural resource decisions that are being made in the late fall. So, I mean, you might not decide to do 6 of them. If you were going to do 6 of them a year, you might not spread them out every other month, but you might do an extra one in the fall, say in October, and then in March. That would be probably help a lot of different kinds of users. And then as you start thinking about applications, there are several groups, for example, EPRI, the guy was here, Electric Power Research Institute, Water Utility Climate Alliance, the USGS Climate Adaptation Science Centers, the NOAA RESAs, where you could start talking about that and get the benefit of them having thought about users for different timescales of climate information and having those connections. So those would be good groups to engage.
Anca?
I just wondered in relation to the question on ocean variables, if there is consensus as to what would be most useful to the community. What we did find is that, well, of course, the data volumes are huge, especially if you're looking at 3D fields. The time resolution also will make a huge difference. And once you start to get below the surface, the spread in the ensemble becomes quite small. as far as we can tell. So there probably is going to be need for compromises. So understanding exactly what's the minimum requirement and the priority for studies based on ocean variables would help. We're trying currently to publish forecasts, ocean variables from seasonal forecasts, and we're struggling to find sufficient information about what would be the critical mass.
Yeah, I do think that I can see how that would be a case where really talking to potential users would be helpful. I mean, I have no idea, you know, for example, what fisheries would want, but it's clear that there are certain aspects of the ocean that matter more to particular species than others. I know there's interest in bottom temperature along the coast, but you do get into questions of whether species move up and down in the water column. I think we had somebody mention that before. And so again, yeah, what would be those more useful variables is something that we need to maybe ask somebody rather than just say, here it is, take it or leave it.
So it has to be a dialogue and try to boil down the 3D structure of the ocean to a subset that can be used for, like in the tropical Pacific, like thermocline depth, or maybe we know that it's an important predictor, but there may be also salinity in certain areas, or so. I think it's an ongoing dialogue.
And I'll just hop in to say, and one that we're going to take on in US CLIVAR in collaboration with the Ocean Carbon Biogeochemistry program in just 2 weeks, and Antonetta Capitandi is co-chairing with Victoria Coles a workshop in Woods Hole that will, for the North American coastlines, be looking at some of the user needs. I think we're going to have some discussion of the value of information for understanding ecology, ecosystem variability, and fisheries movements along the coastlines on daily to decadal timescales. So we have opportunities, I think, to have discussions to illuminate what variables might be really valuable.
I guess it's going to be useful that I'm going to be there then. I think, Jerry?
Yeah, you may have mentioned already, I missed it, but your last point there, how do we coordinate international efforts? There's something called the Decadal Climate Prediction Panel, and a number of us in this workshop are on that. And right now, Steve Yeager and John Robson are the co-chairs. And that is a WCRP activity where you can kind of engage, you know, that community that's more of a research community, not so much an operations community, but that's an international connection that is relevant, I think.
So that does get into that question, which I think I stuck on somewhere, about whether it's better to think of this in terms of extending a seasonal forecast or bringing the decadal down. So if we were thinking this is more of an extension of the seasonal forecast, shouldn't we go more in that, or should we go more in that community?
Well, the initial, I mean,
or does it not matter?
I think the decadal is a kind of generic term at this point. I think it's a legacy from when it formed about, I don't know, 5 or 6 years ago, mainly to come up with coordinated experiments for CMIP that had 10-year hindcast lengths. But actually, the CMIP-6 experiment protocol started out with 5-year hindcast with more ensemble members, and then a lot of groups extended to 10 years. So it's in that ballpark. I think it's beyond 2 years. It could be almost anywhere. But I think right now, you know, advocating for that time scale with that group would be probably well received, since a number of us are involved with this. So, you know, looking at shorter time scales, I think is interesting and relevant.
Yeah, just on the coordination question, there's also a WMO activity to try to build a seamless global data processing and forecasting system, the GDPFS. And there have been guidelines recently written for the centers that will lead on the decadal forecasting. And I think UK Met Office is the lead center and reference that. But they're certainly working hard to figure out how to bring that all into one sort of unified service that is not just the centers, but also connects to all these different countries that don't have as strong climate services around the world. So that's another coordination body, I guess.
Yeah, I mean, the one thing I guess I do tend to worry about a little with that is that the decadal prediction is run once a year, which makes sense for decadal prediction, especially if you're going to run out 5 or 10 years. But if you're trying to get some granular skill on the shorter averaging interval for these leads, you know, is it going to be, I mean, this is kind of a political question I don't pretend to know the answer to, but does it get lost sort of in that push to do the longer runs, right? You can't, it's like, well, okay, I'm starting in November, maybe I'm running twice a year, I'll run out, I'll save more stuff out to 2 or 3 years, but you know, suppose we basically come around and say, well, it should maybe be at least 4 times, or maybe there's a couple particular specific initialization months, which would be really useful. You know, how does that fly with that community? It's all right? You're flexible, okay. Well, I'm good then. Was there somebody else? Otherwise, I think I see it. Anca, I think you have your hand up.
Sorry, me again. I didn't quite understand the suggestion about how to use the information from the decadal prediction panel. Are we talking about analyzing some of the data that's already been collected as part of DCPP to understand what would be an optimal subset? I'm thinking still, I'm fixated on the ocean variables. One thing I do know is that the decadal runs for DCPP, for CMIP6's DCPP, have typically about 10 ensemble members per year in the hindcast, with some notable exceptions. I wondered if looking at the larger ensembles, which may have output enough ocean data, may teach us something about how many ensemble members to save, what variables, at what time frequency. I've come across some people who work in fisheries who wanted some GCM data for small areas of the ocean to drive their regional models, which have fish included in them. But they want 3D ocean variables at the time frequency at which they want to exchange information with their models, not monthly means. So it's a very diverse community of users, of potential users of ocean data, and I think we need to use the data sources that we have at the moment, the repositories, to try and analyze a bit, understand a bit what might be useful to output in this kind of setup, because it is expensive.
Yeah, and this is exactly the kind of discussion that we have to be having right now, because having just finished another phase of CMIP6, and the DCPP experiments you mentioned, of course, are in that archive. I think now is the time you start thinking about, okay, now what do we do next? And this is the kind of thing that the DCPP should be considering for coordinating this kind of activity internationally. And it's not frozen into some mode based on previous CMIP phases or DCPP experiments, but I think now's the time to formulate maybe another round of coordinated experiments where you take these things into account. If Bill's still on, I don't know, member of the DCP panel, maybe he could chime in if he's still there.
Yeah, Jerry, I think that's right. I mean, sort of CMIP6 is more or less in the can. There's some, attention to analyzing those results, but it is a huge resources. Anca points out, the CMIP data request is, very extensive, and there's a lot of, even high frequency 3D ocean data that could be, examined for various purposes that just maybe hasn't been mined yet. And so this is kind of the time frame where the panel is starting to turn its attention to CMIP7 and, sort of various larger issues. So I think that's an excellent suggestion, Jerry.
How does that happen?
Well, the Steve Yeager and John Robson are the co-chairs. They'd have to coordinate. The way this has happened in the past is we have an AGCI session in Aspen. Everybody shows up and we talk about all this stuff, and you try to get representatives from these various communities, and you formulate some kind of experiment design. So I think the thing that's changed a lot since the last time the DCPP tried to do something like this is that this initialized prediction framework has really just been extended to all these different timescales. They've always been there, but I think these different communities that are involved are now more active and more connected than they were before. And I think looking at these different things, at this point, you'd think everything is pretty much on the table for these kinds of discussions, as long as you get people that are involved with this kind of having a voice into how you formulate one of these big coordinated international experiments. So, Bill, we should have a meeting in Aspen.
No complaints.
All right. Any other comments online or in the room? Okay, I have one more slide, which was a little more fill-in. I know things are running a little late, but at least I'll just raise this issue. This would be a good opportunity for people to use the Slack channel to interact a little more on this. And it's the question, what kind of research questions we want to prioritize coming out of this. And so just put a couple down that seem to be pretty obvious. They've come up a number of times. This initialization problem is obviously really important given the limited data that we have. It tends to force us to do relatively short hindcast periods, but of course to get a good sense of the inherent skill and predictability, maybe even in these models, you want to have a longer record. And so that tension doesn't seem to be resolved. And it's interesting to see different strategies come up. And I think that's something which maybe warrants additional focus, or maybe other ways to go. And they may be related to questions of better understanding of some of these processes as well. So that may also tend to drive science, I think. That was the first one here. The second one is kind of related to that, which is which are the processes that we are particularly deficient in for multi-year prediction. It does seem that certainly questions of both sea ice and land processes seem to be potentially limiting our prediction skill. We know there's land memory. We're not sure how much. We don't know exactly what the mechanism is. The reemergence is obviously, our view, but that may be wrong, or there may be other mechanisms. It's just something that's pretty much not really drawn a lot of focus, particularly on these longer multi-year timescales. And then obviously another issue is just the observations itself. We clearly are getting into an era where we may have additional availability of BGC observations, but there's still a question there of how much and where. And then again, the land, we have this fundamental problem, especially below the root zone, that satellites have not been, up till now, really configured to look directly in that layer. They tend to either look at the entire deep layer or the surface. And so the question of how important the vertical structure is, again, remains unanswered to the extent that we don't have those sorts of observations. So that was kind of three off of the top of our head. Just open it up if anybody has particular priorities. I mean, obviously, we have a nice list that the breakouts have put together, but just like, what's your top science goal, I guess?
Yeah, so I think one of the things that's come up several times in the workshop and mentioned most recently this morning by Julia in her talk is, why are these predictable signals that seem to actually be there, why are they so much smaller in the models than the observations? And I think that's a real fundamental research question.
And maybe just adding a little bit onto that is one hypothesis I think for this is that higher resolution might fix this. I've heard Steve Yeager has some results showing this. There's been some work suggesting that atmospheric responses might be higher at to SSTs might be higher at mid-latitude SSTs. I mean, might be higher in higher resolution simulations. So one question related to fixing the signal noise paradox or figuring out what is the issue behind this might be what resolution do we need to be running things at to get skillful predictions from mid-latitude SSTs.
So I'm definitely interested in the how do you initialize multi-year predictions better? And your earlier comments about do you do this across different types of models or in one? I'd say it'd be most useful to do it in one, but if you wanted to train creative new ideas from the university community, it would make the most sense to be able to partner with one of the operational centers or some research center. And so that's to do it in a way that actually helps inform other model, everything that's already going on. So I think for that kind of problem, you can't necessarily have small projects. It's going to have to be more collaborative.
Okay. I think my voice is just about worn out, so that might be, I'm going to hit my hard limit here. All right, well, in that case, I know we're running a little late too. So I want to thank everybody for attending, both online and in person. I think we nudged, got close to 100 at a couple of points, and I think that's pretty good. I mean, this has been an interesting experiment too in hybrid workshops. I hope everybody got a lot out of it. I know I certainly am happy with how things have gone. And you'll be hearing more from us soon. And if you have any additional comments, there's still that Slack channel. So thank you.